data I'm going to be talking about come from this project called Argo project, and the data collected by these cylindrical objects called Argo floats. And these floats would constantly engage in this descent, ascent motion, and the cycle takes about 10 days. But once it goes down to about 2,000 meters, it starts to come up, and in that process it collects temperature and salinity. And once it comes to surface, the data be transmitted. And there are thousands of, and it does this continuously. And there are thousands of floats, 4,000 roughly. Here's a picture of where the floats are a couple of days ago. This picture is renewed every day on the Argo data site, or project site rather. So there are this many floats on that day. You would think that there are a lot of floats, but really, in view of the vastness of the ocean, really, we still have very sparse data. For example, here in the South China Sea, there are only a couple of floats, which is kind of surprising. The floats are free floating. They're not attached to any fixed station, anything like that. So they do move around, perhaps not too much. Now the name Argo came from Greek mythology, in which this person, figure Jason, sailed in a ship of Argo to capture the golden fleece, grown on some winged rams, something. And nowadays we have the Jason satellite, which surveys the ocean surface, the topography of the ocean surface, and the floats look at what happens underneath. Now, this picture shows the growth of the number of profiles. A profile is the set of data that's collected in a cycle. So we have every 10 days there's a cycle. So 3 cycles per float, 4,000 floats, so about 12,000 profiles every month. And as you can see, the number of profiles has doubled from since 2007. At that point, we had about 6,000 profiles. Now it's about 12,000. And the number of observations, so this is a histogram of the number of observations in every profile. And as you can see, the node is around 50 or 60. Now, here's a picture of plots of temperature versus depth at 6 different locations. So every location, the plots are, the profiles collected during the past 10 years or so. Generally speaking, temperature goes down with depth, but at very close places like here, this is a location that's close to the, perhaps close to Antarctica, and the temperature does go down first and then come up a little bit, and afterwards it will continue to go down. And also you notice that the shapes of these curves are distinct. They're different from location, somewhat different from location to location, except perhaps for this one. So all the curves are banded together in these other 5 locations. So we're going to be focusing on the relationship between temperature and depth. Although salinity is also collected, we're not going to address that. That's less important. Temperature is more important. And we're going to take a functional data perspective. we're going to be focusing on estimating, modeling the relationship between temperature and depth, and estimating the mean function, for example. Okay. If you're interested in the Argo data, I can recommend at least two papers. This paper is written by two oceanographers, and this is very widely cited, which talks about the history and generalities of the Argo project and the Argo data. And the data is still not very well known in statistics. So there's at least this paper by Mike Stein and his postdoc, former postdoc, Michael Vasella, who's now at CMU. I learned about Argo data from Michael a couple of years ago when I visited Chicago. So that's at least a place to start. Now, let me talk about data a little bit. So, so the data in the measurements in the profile consists of these elements. So you have spatial location, which is longitude, latitude. You have time, which is day, year, actually hour of the day, which I ignore for now. And number of measurements, temperature and salinity measurements in the profile per cycle. So X denotes salinity, Y denotes temperature, and Pij denotes pressure, and the unit for that is dbar decibar, and that's roughly same as meter, and that's a proxy for depth. Okay. If you have questions about the data, let me know. So we're going to focus, like I said, we're going to focus on temperature here. And for convenience, assume the flows are all identical, so we're going to ignore flow identity and just focus on profile. Okay? Now, so the model for the I profile, this is temperature again, is going to be a mean function, a mean field, plus the zero mean process, plus measurement error. And this zero mean process captures the dependency in depth, spatial location, and time. Right? So it's a really high dimensional process. The mean field is something, of course, everybody's interested in, especially practitioners. If you want to know if there's global warming, then the question to ask is whether this function changes when time changes. Right? So right now we're going to discuss a little bit of inference on the mean field, and in parts 2 and 3 we'll talk about the kind of models that are feasible for Z. Okay? So the 3 parts are connected this way. I already mentioned that we're going to approach the inference of the mean field from a functional data perspective, and we'll estimate this as a function of pressure. P is a strange notation for an argument of function, but it stands for pressure in this case, and it makes sense. We need to do some modeling due to the high dimensionality of the problem. So we're going to assume a very naive model. The mean is equal to baseline mean, which only depends on spatial location, but not on time, not on day or year. And here, the effects of day and year are assumed to be additive effects here, which may not be entirely reasonable, but that is sort of the best we can do right now because of the computational challenges. So mean D, the day effect, is modeled in terms of a periodic function, which sort of makes sense. It models the seasonal effect within the year. And then the year effect is just modeled very simply by this very simple quadratic model. It could be more complicated, but because we don't have many years of data, we have 10 years or 12 years of good data. So a qubit model seems reasonable, but in time we will try to make this more complicated, more involved. Now, so since I'm going to be taking a functional data perspective, I'm going to be doing non-parametric estimation. And I need to assume that these are all functions in P, in depth. So I'm going to assume that these functions are smooth, at least 2 times differentiable. And I'm going to put all of these elements in a big sum of squares, like this. So here I'm assuming a fixed location, S naught. And so Yij is the profile that was observed at the location Si. So we'll make sure that I only include profiles for which the location is close, relatively close to S naught, where my estimation takes place. So I'm using the kernel function here to determine what data to include. Okay. Now these terms are exactly what I had here, except I'm now using different notation. So beta d is this periodic function, and beta y is this cubic function. Now, to estimate the grand mean, which is this guy here, I'm going to do a Taylor expansion, function Taylor expansion, to account for the fact that Yij is observed at Si instead of S0. Okay. Now, if Pij is not a vector, this is one point, P. I think everybody will recognize what this is. This is local linear regression. Well, the complication here is I have a vector piece, that's just fixed P. And I want to make sure that these functions are smooth. So the functions, the quantities in red are functions, and they're the ones I'm estimating. So I'm assuming these functions are smooth, so let me just add a penalty to all the betas. So as you can see, this is a kind of a hybrid approach which combines local linear regression, kernel local linear regression, and the penalized approach. Right? And the minimization takes place in a function space, and so far we tried a solo space, and the penalty is simply the integral of the square second derivatives, and I have a whole bunch of those. So in order to justify local linear estimation, I need for the mean function to be Fréchet differentiable, which we do. And this approach leads to more efficient use of really sparse data in this non-parametric problem. And moreover, the information about the direction, the speed of temperature change is actually captured by the gradient. So the gradient of the mean function comes out as a byproduct in non-parametric estimation, and it's actually useful. It has meaningful physical interpretations, and I'll show you a picture in a moment. Of course, it's extremely challenging to really select the the smoothing parameters, the H, the lambdas, in a principled way. I'll talk a little bit about that in a minute. But we managed to sort of improvise and come up with reasonable choices, somewhat manually, if you like. And so we're just going to show you a picture of that. Here, this is depth from 0 to 2,000 meters below. And this is day of the year for one particular year, I think 2016. So this is a location in the South Pacific Ocean between Australia, Antarctica, and Argentina. And here are other Q estimates. So at every location there is such a picture. Okay. Now let me show you a picture of the gradient that came out of local linear estimation. Remember, we had a function in T, so for every P there's such a picture. This is the gradient field, and you see these arrows. These are directions of the gradient, so directions where temperature change is the fastest at every location. And the color here is a heat map of the magnitude of the gradient. Okay? Because I have such a picture for every pressure level, I can play a movie. So this is a movie of that as the depth changes. All right. Now, intuitively, there's some connection between how quickly temperature changes, that's the magnitude of the gradient, and the speed of ocean currents. I don't know what exactly the connection is, but intuitively there is such a connection. So on the upper left, this is a satellite picture of sea surface current speed. And using the same coloring scheme, I'm plotting three plots of the gradient field at three different depths, 300, 400, 500 meters. And somehow they're connected. For example, the details that you see here, you also see on the satellite picture. Now, unlike the satellite picture, which can only look at current speed on the ocean surface, we can go down below the ocean and look at the gradient fields for temperature change. So there's no objective so far. I'm really at a stage where I'm just exploring data, understanding data, and trying to explore the different methodology. And I will mention a little bit the objective. I'm far from the objective. Maybe in 5 years I can answer that question. So what's ongoing? We're trying to, like I said, to understand data and experiment with different approaches. The smoothing parameter selection is the biggest challenge we're facing right now. The solution of the approach I showed you earlier is a natural slowing, and there is a way to compute that, but still the computations are very challenging. Grace also taught us how to use the Lee one-mile formula to compute the optimal smoothing parameter. But again, it's very challenging. We're leaving a pro out every time. And dimensionality of the problem is so high with 6 different functions that we estimate. So we're still very much trying to grapple with that.
So the smoothing function for each variable, and you're going to have one for depth, because depth varies.
So it's, go back here. Right, so these are the functions that we estimate. And there is a lambda for each one of these. And of course, we have this h. So lots of smooth parameters to choose. Okay. Now, come back to what Dan said, it's really scientific issues that are the most important here. We want to be able to take part in climate research ultimately. So what we have to do at this point is to, for example, go to scripts and talk to the scientists. And I view the work we've done so far as preparation for that, because they're very, very smart people. And if we don't have something to show for it, something to convince these people that we can contribute, they will not talk to you. And so I feel that we're close to the stage where we can go and say, can we come and chat? Like maybe they will be interested, and in a couple of years I can come back and tell you what we have accomplished in terms of real science. But so far, this is just, so this is just a lot of exploration and trying to feel things out. Okay, so this is the first part of the talk. Now, the second part has to do with thinking about what are some of the suitable models we can use for Z to capture dependence. The first model comes to mind, which is really not a model, but stationarity. Can we use a stationary process to do this? Recall that I'm taking a functional data perspective. So let's say we have a process indexed by R. Now in our problem, it's really indexed by R raised to the many powers. But let's just make life simple and consider a class of processes indexed by T. So for every T, xt is a function. It's called a random element in Hilbert space. Right? Assume mean zero, finite variance. Define the cross-covariance operator. This notation, Tesla product notation is just outer product. So you can think about a finite dimensional situation. This is just, x of s times x of t transpose. This is cross-covariance matrix, and it's called operator here because H could be infinite dimensional. And here I'm going to assume that X is second order stationary, meaning the cross-covariance operator only depends on S minus T. Right? And now denote the stationary covariance by K. The K of H is the cross-covariance between X of S and X of S plus H. So what are properties of H and what are some of the possible models? Seems a complicated question. Well, fortunately, we have math. That's what math is good for. We have what's called Bachner's theorem, which would give us all the models we need, all the models in the world. And let's consider the simplest case where H is really one-dimensional. H is space complex numbers. And then this is what you learn in a probability class. This is a representation of characteristic function. Right? Now, suppose H is d-dimensional C to the D, then things are more complicated. So for example, the non-negativity that we have here as real numbers, now it is non-negativity for matrix. Right? Everything else remains the same. In that case, we still have Occam's theorem, which looks exactly like before, except that mu here is going to be a matrix of sign measures that are non-negative definite. Okay. Now, so next thing I'm going to do is to say, let's go to a bonifying function space and see what happens. And really, the story doesn't change very much. It's there's some background information you need to know about infinite dimensional spaces. So here, K is a collection of trace class operators with whose singular values are similar. Right? And we have non-negativity, as in the matrix case, it was operator non-negativity. Continuity, we have to say what we mean by that. So this is in terms of the tracing one as 0. And then we have this Blockworth representation. Right? Again, mu here is going to be more complicated. So mu is a operator value measure. We don't have to know what it is. The important message here is that we can write down every possible K that satisfies these properties. Relating this back to our problem, so we have a process x taking value in some over space H. We assume it's mean squared continuous, right? And we assume it's stationary. So in that case, the stationary covariance can be represented like this. So whatever mu you plug in, mu that satisfies what's described here. I've left out some details. Whatever mu, admissible mu you plug in, you have a stationary covariance operator. Moreover, suppose these kh is integrable, or the trace norm k is integrable, then you can do Fourier inversion and compute a bounded density for these for the cross-covariance operator. Yes.
Mu is trace class.
Yes, I'm assuming everything is trace class, and so I start out with trace class.
In the Blockworth representation, this mu.
Yes. Trace class. Yes. So there's an issue of how to define this. If you're not in trace class, this is very tricky to define. So that's really part of the definition of this, what this integral means. We can talk more about this if you're interested. I don't want to bore everybody. Yes.
Tx is inner product.
Which one?
This e to the itx. This tx is inner product.
Right. So I'm assuming that T is in R. So if T is RD, then this is going to be inner product. Trying to make the notation simple. Now, so is Mac? So people in functional data have looked at the case where there's a density, that a covariance operator has a density, and they, discussed how to estimate density, mostly using still the periodigram-based approach, extensions of that from time series analysis. So there are these papers if you're interested. In fact, the mathematicians have looked at cases of this problem. You just have to figure out they're connected to what we do here. So these are papers in applied harmonic analysis. And if you look at a title of the papers, it's not clear how, how they're connected to our problem. And if you look at content, they deal with very abstract settings. And somehow you have to translate what they do to the kind of notation and setting we're used to. Anyway, so now, how much time do I have? Okay. So we talked about stationarity. Stationarity is great, but it's kind of limited, very strict and model. How do we go beyond stationarity? So first, there's something called intrinsic stationarity, which is my title, and that's defined as follows. So let's consider a sign measure with finite support. So lambda is a measure that has mass c sub I at point t sub I. Okay? And for every function f, define f of t plus lambda as this convolution, which is sum of c sub I f of t plus b sub I. So for instance, if lambda is delta 0 minus delta minus 1, then this is just a differencing operation. So you can express differencing operations in terms of convolutions like this. And lambda k denotes the collection of measures with finite supports, sign measure rather, that annihilates polynomials at degree k. So, for instance, this measure here annihilates constants, function of constants, so it's in lambda 0. This annihilates any linear function that's in lambda 1, etc., etc. Okay? So, George Matheron introduced the notion of stationarity after differencing. And he referred to such process as intrinsic random function, IRF. Right? In particular, process which is stationary after one-time differencing, like when you subtract xt minus 1 from xt, it becomes a stationary process. Then it's called an intrinsically stationary process. And this is intrinsic stationarity is widely assumed in Greek. And Matheron was the person who, sort of coined the term creeping. He didn't invent creeping. He's sort of was the person who put everything together. He knew the theory as well as applications. Now, so we say xt is IRFK if this process x becomes stationary after we applied the differencing based on lambda. So xt plus lambda is stationary. For all lambda in lambda k, then xt is called IRFK. Now, the cross-covariance operator, of course, is simply this for this particular lambda, where C here is the cross-covariance of x. Right, so here we're assuming that this expression only depends on s minus t. That's what stationarity means. So this is kind of like linear basis function Grace mentioned this morning.
We
Yes.
have a notion for a second order stationarity, or the second differences are stationary.
Oh yeah, so this is general, so this is lambda k. So for every k, this is defined. Now, so we said, for our k, we have that this function is only depending on s minus t. It turns out that there exists a k, which is called generalized covariance, which satisfies this relationship. So k acts like the covariance function, but it's really not the original covariance function. It's called generalized covariance by Matheron. And this is a somewhat complicated result. It's not especially deep, but it's if you haven't seen the proof, you will not find the proof very easily. It took us a long time to figure this out. Matheron mentioned this in his paper. He didn't provide proof. Nobody understood it. Everybody accepted that. And we finally proved it. But I think maybe Matheron felt it was very easy. I don't know. Now, as in the ordinary stationary case, one can write down a representation that's similar to Bachner's representation, like this. This looks somewhat different from the original Bachner's representation, that we have this quantity here, which will, allow us to have something, a measure that's exploding at zero, and for which the interval is still well defined. So I will not get into details of this, only that this is related to the Levy-Kinchin representation of infinitely divisible distributions of the characteristic function. One can also write down a spectral representation for IRF case, and this is a generalization of Primaire's spectral representation for stationary processes. Okay. Some examples. So let's take a very simple case where the Hilbert space is actually a real line. The fractional grounding motion introduced by Mandelbrot has this covariance. H here is called Hurst index. H measures the smoothness of the path of the process. Has many appealing properties. It's self-similar, stationary increments, and so on. So at the end, fractional grounding motion is actually RF0. Generalized covariance is this quantity, which is the minus semi-variogram. And one can write down toy examples of IRF processes when H is a function space. For example, this one, which kind of looks like a Hundon-Laev kind of expansion. So these phi's are basis functions. The ZJs are independent fractional grounding motions. And the lambdas are sort of eigenvalues. And for this, the generalized covariance operator is that. Now I think I have a bit more time because we didn't start. My talk didn't start at 2:10, so I have a bit more time because I have part 3. I will just go over it very quickly. So that's the original paper Matthew wrote in the English language journal. Yeah, maybe the French journals are not really accessible. So this is a paper that everyone can read in events of applicability. If you understand what he says, good luck. And eventually you have to go back to Gilfan and the Langton's book on generalized functions to know what the details of what's needed in the proof of generalized covariance. This paper is actually very helpful. It's a bit terse again. It really talks about a lot of things I presented here. Now the third part is my take of think globally, act locally. So I talked about global stationarity or global intrinsic stationarity. Those are more general than ordinary stationarity, but those are still rather restrictive. So I'd like to speak very briefly, perhaps in 5 minutes, about local stationarity. So let's consider a process xt. Again, for every t, xt is an element of a function space. So here I want to explore what happens when we conduct differencing locally at a point t. So let's fix t and see what happens when we do this as epsilon goes to 0. Suppose x has continuous sample paths, you'll say this will go to 0. But if we blow things up by multiplying something, suitable normalizing constant, it can go to a limit. Right? So this is very much like what we do when we take derivatives. So for example, if we have a return model, then when we conduct this operation, local differencing and then normalization, the limit is going to be fractional ground motion, and the Hurst index is actually this smoothing parameter nu. And if BH is fractional ground motion, then something similar happens. The normalization here depends on the Hurst index. The limit is still FBM. So FBM has a domain retraction in a way. Now, if X is multifractional ground motion, NBM, with Hurst function H, then at the point T, the normalization involves H of T. Here, H is same for every T, but since we have a Hurst function here that depends on T, what is multifractional ground motion? Well, it's kind of like fractional ground motion, except the Hurst function changes with T. And now here's a similar path for NBM with Hurst function that looks like this. When the value of the Hurst function is large, then the path is smooth. When it's small, the path is rugged. So I don't have time to really go through all my slides. I'm just going to quickly give you a summary of what's in the remaining slides. I'm going to consider this differencing operation locally for general lambda, not just the order one differencing operation. I'm gonna take the lambda in lambda k. And ask the question, suppose I can find normalization such that this generalized differencing converges to a limit. Okay? What properties must this limit have? In a nutshell, the limit is going to be self-similar because of the scaling. Self-similar. It's going to be IRF. So this is a notion of local intrinsic stationarity. And just like, global intrinsic stationarity, I can have a representation for all the processes that are limits of this kind. Right. I think Dennis is going to scold me if I continue. So let me just stop here. Perhaps 30 seconds. So I have a toy example that I can show you. So let's say we have, sorry. Right, so this is really a function space. I'll tackle it. This is a process I constructed toy example. The phi j's are again basis functions, and these zj's are I being multidirectional ground in motion. And how do we conduct inference on this process? Right? So what we could do is to do projection. So here we have a process we can project the process on a function h. We're back to the real case. And for the real case, actually I've written a paper that talks about how to estimate the Hurst function. And we have a infill asymptotic result. If we have data observed on a fixed grid, then it is possible to prove a minimax rate, provided that the candidate functions are in the Holder class. The rate is very similar to what you would see in non-parametric regression, with the exception of this extra square log term. And if you're interested in this, it's going to be in the paper that are appearing next year. The first paper here is the paper about sort of tangent fields, which are the limits of the difference process in the one-step difference. So the person who studied this was Faulkner, and our results for general differencing can be viewed as an extension of that. So that's a useful reference. Thank you very much.
Yes.
So, but it looks like the negative of something. So this is basically a negative definite function.
So it's a generalized covariance. People describe it as conditionally yeah. So in the case of I0, take generalized covariance minus the minus of some division.
Because you say negative of something is symmetric.
Yes, exactly.
Okay, learn what's
Well, it seems to me there should be great scientific interest in this data. I mean, it must be related to large-scale movement of the ocean that's related to climate, the constellation,
Yes,
you
absolutely.
build it in a physical model of the physics of the ocean, you should have some
Absolutely. So here, sort of what I presented is really, non-parametric estimation, brute force approach. Doesn't involve any physics, doesn't have differential equations. So to be able to do that, we have to talk to specialists, to physicists, oceanographers. That will be our next step. He absolutely will have to say
mind if you learn, don't fight percentages, right? So you need time, just give it time, especially when I have one paper under revision for the annals. Make it quiet. So thanks Tailen for one talk. So time is a little delayed, so that's okay. We just probably just keep moving everything scheduled for 5 or 10 minutes. So we'll figure out how it goes. Our next speaker is a really famous person in machine learning. Okay? Alex Smola, who actually will be starting with page 1 half. He got PhD in physics. He got PhD in physics, which my physics means everything in my generation, right? Chemistry is called applied physics. Biology is physics, but wherever can move, right? Mathematics is simply a tool for physics. So physics is everything. So he got degree in physics, that's bias anyway, from University of Technology from Munich, and got PhD from University of Technology in Berlin. Then he went to academic job, I think somewhere in Australia. Australian National University, being a professor, doing really great. 2008 he went to Yahoo, and then 2016 became director of machine learning and Amazon Web Service. I personal bias, I don't like the word machine learning. I think it's more like automatic learning. Machine don't learn anything. So anyway, by that, interesting thing is when you look at his website, my final comment, you go to his website, give a name and address. Without saying anything, you say, I'm currently not looking for a PhD student. So see, you must do lots of confidence rather than say how wonderful I am. You say, I don't need more PhD. So by that, let's welcome Alex.
So thanks for the kind word and the introduction. The reason why I'm not looking for PhD students is simply that Amazon doesn't take PhD students. And yeah, sorry, nobody wasted their time on that. So this talk forced me to, well, think back a little bit. You know, we've been doing some work on graphs, mostly my team in Shanghai has. So a lot of the results are due to Hsing, and Mingyue Wang, also part of the team in Palo Alto. But this talk sort of forced me to go back and look at, you know, what did we do with graphs before? And so, okay, did a bit of a bait and switch on you because I say, well, you know, from features to kernels to features back in, and I will take a little bit of, you know, engineering on you in the end. So talking about, you know, framework backdrop, as you said, graph backdrop partitioning, and you know, stuff that are involved in this. And so, but let's start with something very non-threatening. Okay, well, okay, yeah, Russian politicians. Okay, sorry, not threatening, maybe the wrong word, but so they do stuff with each other, right? And so you might want to do interesting things with that network. So for instance, you might want to find out what the relationship is between the vertices. You might want to find out, you know, what the attributes of the particular vertex are. So such as, you know, you get some features, maybe you get some additional data, maybe you know the net worth of that person, maybe you know what time they send messages to each other and so on. And well, maybe in a slightly different setting, you know, you might have a social recommender. Hey, you might want to take a bribe from that guy too, or well, don't trust this one. Or maybe, you know, use additional data, maybe biographical data to combine this. So that's the kind of fun that you might want to do with graphs. You can also, you know, use that for drug discovery and so on. So the big graphs are really everywhere. To some extent, I would argue that probably we have one of the largest places graphs available. Yeah, I know. I didn't make that graph, but yeah, I would have wanted to put him in, but last time I did this after that, he got elected. That was 2015 in the KDB talk. I made fun of Trump and he got elected, so it went badly. I don't know why I have this. But
was that based on real data?
No, this is just like, you know, this is an interaction network of Russian politicians that I got somewhere, but this is just to motivate the problem so far. So what do we really have? Well, we have some vertices with attributes and edges. with attributes, and then we have an estimation problem, namely given some vertex labels, we estimate the remaining ones. So for instance, who can I trust, who I cannot trust, or given some attributes, well, can I make some more? So for instance, which additional edges should I add? Maybe they're timestamped and so on. So, and let's just simplify this even further. Regression on a graph. So this is like sort of vertex labels, like yi and y, and I want to find some function such that the function is kind of taking this a little bit liberally because I have fixed number of vertices. At least in the simplest case, it's really a vector. But let me just call it a function for now, which maps the vertex ID into fi. And then I want to, for instance, minimize the loss, like a least squares loss. So fi minus yi for wherever. And so that gets me to a number of problems, like how do I infer the function values on previously unseen vertices, and how do I even define smoothness on this? And so one thing that I could do is I could just say, well, let me do feature engineering, right? So I have maybe some linear function, fi is w transpose vi plus b, and all the intelligence is now in those vertex features. And I could do a number of things, like the number of neighbors tells me something about how important somebody is. So I could just look at the degree, maybe the degree of the neighbors and other things. I could look at a lot of different subgraphs that I can get. I mean, let's say maybe I take a 5-hop subgraph and I get an entire vector of that. And that's walk to vec, for instance, and people have this. Or I can just overall fingerprint the k-step neighborhood, and actually the Weisfeld-Lehmann algorithm is a really great tool for that. And Carsten Burkhardt and Shabashidze in their prize-winning paper, they use that to very efficiently compute graph graphs. So we'll get to the Weisfeld-Lehmann algorithm in a little bit, but it's actually an amazingly clever algorithm. Or I can just use linear algebra heuristics. It's not uncommon. Maybe I take my graph connectivity matrix and I factorize it, and maybe I take the leading few eigenvectors and I get some idea of what might be in there. Or I use PageRank, and PageRank turned out to be a multi-billion-dollar heuristic, namely the amazing heuristic that led to Google web search. And so I can do that. As an alternative, I can look at smoothness over edges. So I basically compare with some function gamma adjacent vertices, or maybe look a little bit further. And I can use a path smoothing. So basically the fielder vector and so on. Jump did some interesting work on that. So I can basically sum over I and j if I minus j squared, and then by simple trigonometry, that's just f transpose d minus gf. Okay, forward. And if I don't like L2, I can try an L1 version. And so Fuchsian 1 and Line to Chirani, and I happen to also sit in on the meetings, but it was really Fuchsian's work. You can do trend filtering on graphs, and you can look at higher order derivatives there. And this works quite well, right? I mean, it's this. So basically, at least you can construct data sets and situations where the L1 version beats the L2 version. Okay, so nice story, but it's expensive. So let's take a little bit of a detour. Once upon a time, there were kernels. So what does the graphical clustering have to do with kernels? Well, I guess that's the obvious part, namely, so what I can do is I can look at smoothness, and since I can use the graphical clustering as a measure for smoothness, well, okay, I can, maybe think whether I could design some kernels based on that. And this, generalizes the finite differences, for instance, a mesh, you have, the